It's an honor to be here. Thank you very much for inviting me. And to anyone who's in the other rooms watching, hi to you too. You often get left out, I'm sure. When I first proposed this talk, it was not intended as a keynote. It was intended for a self-selecting group of people who might be interested in hearing about the updates that I'm going to talk about. And when they asked me about a month ago to turn it into a keynote, I had to kind of radically reimagine it. So I'm going to make the assumption that there are people in here who don't really know that much about WebAssembly, don't really care that much about WebAssembly. Isn't that browser technology to kill JavaScript? It is not, right? It is a much bigger vision. So I'm going to start by motivating the platform and the effort and the initiatives, and I will end with a discussion of where we are and kind of where we're going in that sense. Before I do that, though, there's probably the more relevant question, who the hell am I? And so I'm going to start there and talk a little bit about some of the background work that I've done that I think predisposed me to being attuned to some of the things that were going on. Because I've been following WebAssembly way back before it was WebAssembly, back in the ASM.js days. Thomas Steiner at Google has a new WebAssembly-based podcast, and he just did a nice interview about the work that led up to WebAssembly, if you're interested in that history. But I wrote the WebAssembly definitive guide for O'Reilly, and before anybody asks, it is based on my dogs. And I can't prove this, but I've been told I'm the only O'Reilly author who ever got to choose the animal. I just asked. And when they asked why, I said, well, because my dogs are Norwich Terriers, and they are small, fast, and portable as well. I'm also currently the editor for the WebAssembly Shortcuts, which if you are new to this and don't want to dive into a whole book, this is a new thing that I was skeptical would work well, but it's actually turning out really nicely. Small little nuggets that come out weekly. Every Tuesday, a new one comes out that focuses on tangible things to do, not a lot of the theory. So that might be a fun way to get into it if you're interested as well. But let me go back a little bit in time. The second job that I had out of college was at a company called Autometric. You will not have heard of it. They were bought by Boeing and basically absorbed into the behemoth. But they were a fun little company. They helped NASA decide where to land on the moon using photogrammetry. And what I worked on there was the first whole Earth commercial visualization environment. So think Google Earth, but in 1994. And if you weren't born in 1994, shut up. I don't want to hear it. But it was really exciting, because even back then, we were dealing with terabytes of terrain information, hyperspectral imagery. We had a whole satellite modeling thing. So you could imagine geocentric satellite orbits and look at the coverage on the Earth and things. The last project that I did for them was to pull video frames off of Predator drones. Before they had guns, they just had cameras. And we would warp them to the Earth. So you could have updated Earth imagery on top of commercial and other kind of satellite imagery. It was also cool because a year before the Gang of Four book came out, the entire user interface was based on the command pattern, influenced by some thinking that Doug Young at SGI had done. And SGI was key to our work, because back then, that was the only way to do anything with this amount of data and these kind of graphics. Funny story, somebody broke into our building and stole all the computers on the first floor except the SGIs, because they had no idea what they were or how to fence them. Anyway, the point here is, within a couple of years of us releasing this software, it ran on a PC with a GPU. And that was my early indication of the power of hardware in terms of speeding things up, and how you didn't really have to do all that much if the libraries and the frameworks and everything kind of took care of that for you. Another thing I'll point out here is, this is about when Hot Java came out. I was on the Java Advanced Imaging Working Group for a very brief period of time. I didn't do anything useful there. But at the same time, this is also when JavaScript and DHTML really started coming out. And my roommate said he was interested in learning it. And I'm a young, cocky C++ programmer doing stuff like this. And I said to him, oh, that's cute. Enjoy your career as a menu engineer. Because at the time, that's what it meant to be a JavaScript programmer. I am happy to say I have ego on my face these days, as you will see a little bit later. The next thing I want to talk briefly about is a company I helped found in 1999 called Parabon. And this was an internet distributed computing platform. So think SETI at home, but rather than downloading just data, you could download applications as well. And so we built the platform, the runtime engine, which ran on 8 different platforms in 1999 and 2000. Pretty proud of that. The client APIs, and then a bunch of vertical applications on top of that. So we had Monte Carlo-based digital rendering systems. We had a genetic algorithm-based feature selection for an exhaustive regression search. We were able to do gene sequence comparisons with linear scalability at the time. Even the rock stars like Celera Genomics couldn't do that because they were trying to send the data around all these different places. And this was my first real exposure to the idea of the cost of computation. Because most organizations don't buy enough computers. If they don't keep them running all the time, the accountants get pissed off and say you can't buy that many computers. And so they don't buy enough. And then there's an opportunity cost in terms of what it is that they're actually trying to do. So we had pharmaceutical companies and whatnot trying to find why certain things would work in some ways and not others. And they just didn't, they were doing manual feature selection at the time, and they weren't selecting for the right features. But when we gave them the capacity to look at more of their data, the answer just came out. So when you had a problem that fit into a situation like this with marginal computation, elastic supply, then you could basically buy the computation that you needed to solve the problem and then stop it. So keep in mind, this is pre-cloud by many years. Obviously, it was also a reductive, embarrassingly parallel-only kind of system. But that was when I first started to realize the importance of the concept of the cost of computation. So my question to you, and it's a rhetorical question, you don't really need to answer, is what programming language would you choose for your next project? And the answer is obviously, of course, it depends. Right? It depends on the business requirements. It depends on security requirements. It depends on the deployment requirements. It depends on lots of things. So when we think of ourselves as JavaScript programmers, Haskell programmers, whatever, we're not necessarily aligning ourselves to all the different kinds of problems we could solve. If we think of ourselves as problem solvers, then we could try to find the right match to the right language, to the right problem, because there are just some things that are inconceivable, like doing machine learning with JavaScript, right? But the TensorFlow team did some really interesting things in one approach towards solving this problem. Because obviously JavaScript is not a super numeric-oriented language, and it needs hardware acceleration to do this kind of stuff well. And so the idea of extending the browser with the capacity to do this kind of stuff is just from Dr. Fielding's thesis, the optional code-on-demand extensibility capability. But how do we actually make it work? How do we make it work so that it performs well? Well, they built a really clean, layered API system. So the ops API is an eager execution environment as opposed to the data graph flow of TensorFlow proper. And then influenced by Keras, they built a layers API on top of it. So developers could build very nice complex neural network structures just using a very simple model. But then they went and implemented the backend multiple times. So you, the application developer, don't have to write feature-tested code that says, am I running in a browser? Am I running in Node? Do I have a GPU available to me? Those kinds of questions complicate the expression of what it is you're trying to do. And so instead, they just have these pluggable backends. When at Autometric, our code went from running on Silicon graphics workstations to running on PCs with GPUs, a lot of people in the scientific community at the time said, why do we have to still buy these stupid workstations? Why can't we do what the game and graphics people do? And so they started using the shader languages to pretend like they were doing 3D graphics. And that's what the in-browser WebGL-based backend does. All browsers basically support WebGL. We have no direct access, or at least at the time, no direct access to the GPU. WebGPU is an emerging standard. But they pretended like they're doing 3D graphics and were able to speed things up. So the implementations that they had were a CPU-based one that was just JavaScript, that just ran on the CPU, that ran everywhere badly. Then there was also, if you were running in a browser that did have WebGL support, you'd be able to take advantage of that. But that's a configuration thing on the back end. That's not something that you have to worry about. If you're running in Node, you may be running on a server that doesn't have a GPU, but has a nice modern CPU that has vectorizing instruction sets and can do better than a more generic notion of the CPU. Or maybe you're running on a desktop machine that has access to a GPU, or you're running in the cloud and have access to tensor processing units or things like that. The point is, you get to build these things, your application, against the stable APIs, and the back end gets swapped out for you. Excuse me. So that's one approach to this, and it has amazing results. So the plain JavaScript on a CPU for this facial detection task, or whatever it was, I can't remember, took about 3.3 seconds to run. The same application, unmodified, running on integrated graphics on, say, like a MacBook Pro, MacBook Air, something like that, could be sped up to 49 milliseconds. And if you ran on a beefy box with a pretty decent CPU, or GPU, excuse me, you get it down to 5 milliseconds. If you ran it on a node machine with no GPU but nice modern CPU, then you could get it down to 87 milliseconds. And if you had access to native libraries and whatnot, we could have up to a 1,000-fold increase in the performance without changing the application. That's a very elegant solution. The problem is Google had to build 5, 6, 7 backends in order to make it happen. And that's not something that's going to happen very often. When I was at Parabon, one of the clients that used our system was a NASA researcher who had a thermospheric simulation that ran for like 9 months on his hardware. He ported his Fortran to Java, which I promise you in 1999 and 2000 was much slower than Fortran. It took him about a week to port the numerics part. He was able to launch his job from Greenbelt, Maryland, get on a plane, fly to San Francisco, and get his results in his hotel. So he was willing to put in the effort of rewriting parts of his code for that kind of speed up. But these days, nobody else is going to do that, right? If you have some kind of runtime platform environment and you say, okay, but in order to use this, you have to rewrite to something else, people are going to be like, no, no thanks. So WebAssembly represents another aspect of that. And in its original form that came out in 2017, called the minimum viable product, there were a lot of things that were left off the table. No threads, no garbage collection. The only data type that it really supported were numbers. No strings, no dictionaries, no associative memory of any kind. But it was a compilation target, a stack machine, that was able to easily and quickly convert things at runtime for near-native performance. It was expressed in terms of binary modules, so it's faster and easier to validate and distribute across the network. And they took the work that had been done for WebGL around typed arrays and used that as the basis of emulating linear memory for porting C and C++ applications to run in the browser for doing things like pointer arithmetic. You wouldn't have been able to do that without typed arrays in an easy kind of way. But what they also did is they separated the stack from the heap. And so it was this security isolated environment, and that gave us, even with all these limitations, some amazing capabilities. So shortly after TensorFlow.js was released, the team built a WebAssembly-based backend. And you may say to yourself, why would you do that? Well, the answer is, when you look at what it was able to do across a wide range of hardware platforms, anything from an iPhone X to an XS to a Pixel 3 to desktop Linux or MacBook notebooks, the WebAssembly version was able to, in many cases, keep up with the hardware accelerated one. And for some models, because of the asynchronous nature of sending data down to the GPUs and everything, if the model fit in memory and you could just do it on the CPU, it would end up being a little bit faster. But what I want you to realize is building the WebAssembly backend for this meant recompiling a C++ program, right? They didn't have to write it from scratch. And so that was a big step moving forward. Now, I want to show you a couple quick demos of what this does for us, just so we have some idea of the scope of the use cases. Has anybody used JQ, the command line tool? Fantastic tool for taking like the JSON output of a command and just stripping off some of the elements without having even to write scripts. So this guy, Robert Abou-Khalil, who has a great set of resources called Leveling Up with WebAssembly, as a showcase, took the JQ command, which was written in relatively clean, simple, portable C, and recompiled it so to be able to run within the browser. So on the left, we have some JSON, and you see we're selecting off the first element, but it's interactive, and you could say, give me the email addresses of all the elements, and it's able to do that. Now, there's absolutely no reason this could not have been written in JavaScript. The point is, why? Why rewrite code that we don't need to? So the next thing that kind of caught my attention is when the Unity engine was ported to WebAssembly, and therefore anything that ran on top of it would run. And if you may recall, I don't remember how many years ago, 5 or 6 years ago, this was Apple's showcase for the hardware acceleration and everything on the iPads and the iPhones. But it is now also able to run in the browser in a portable, cross-platform kind of way. And you probably can't hear it too well, but there's some background noises that are very, the fish and the water and everything. It's just a compelling idea of taking something like the Unity engine and making it portable. And zero installation, which is another big part of this, right? My favorite example is what Colin Eberhardt did to extend the capabilities of the platform. Hold on to your hats. He used WebRTC to get permissioned access to the video camera. He then used OpenCV, compiled to WebAssembly, to flatten the image so that he could then use TensorFlow, compiled to WebAssembly, not TensorFlow.js, but TensorFlow, to extract the givens, take those givens, hand it off to a Rust-based Sudoku solver, solve the Sudoku, return the results, and use OpenCV to render the result back on the video frames in real time with, again, capabilities that the browser would not have been able to have otherwise. So another use case beyond reuse is extending the capabilities of the platform without having to go get all the major browser vendors to agree. And they're only going to agree if the 400, 500 plus member organizations at the W3C agree. So to extend the platform with some kind of capability that JavaScript itself is not necessarily a great implementation engine for, you're talking years before you're going to have that capability to you. And this is something that can be done rather quickly. This is a fun little example. You won't be able to run this if you get the slides, but this is an SVG image with embedded JavaScript calling into a physics engine, deciding where to place the sand particles. And obviously, SVG supports animation, so we can flip gravity. But here's the thing. Those particles are DOM elements. And if you look at the inspector, you can see them being updated by the physics engine. So this is not your parents' web experience. Today, there's going to be a talk about Blazor. And one of the interesting things about Blazor is WebAssembly is just an implementation detail. You don't have to know or care really about WebAssembly in order to benefit from it. And here we have an example of a single-page application. It's stateful, right? You can access APIs like the Fetch API and go out and grab things. And if I showed you the network view of that, you'll see that it's downloading a bunch of DLLs running in the browser on top of the Mono platform that has been compiled to WebAssembly. So you can see there's no single use case. There's all these different kinds of use cases. Why does Jupyter Notebooks spin up a backend server? It's because Python doesn't run in the browser. Or does it? Here we have PyScript using MicroPython, which is something like a 300 kilobyte Python 3 implementation. And you can just say, hey, run this Python code in the browser, and it will. But more impressively, how about run some NumPy-based Python with the native libraries compiled to WebAssembly and get the hardware, not the hardware, but the speed up that does for you as well above regular old Python. How about running a database in the browser? So this is DuckDB running in the browser. Imagine having the ability to write structured graphics on something more than IndexedDB, and then be able to use regular SQL queries and prepared statements and stuff like that. We've got people using WebAssembly for extending databases with user-defined functions, right? So you can just push code down into the database, and they're able to run it. Or how about just running Linux, right? This is Linux. Again, I don't have a lot of time, so I'm not going to show you, but go play with it, right? You can run Python. You can compile code. You can use native tools. If you need networking, there are ways of triggering WebVM to do that. That uses a technology called ChirpJ. Cheer-P, which is a compiler, an LLVM-based compiler that produces some WebAssembly backend from that. And finally, the part that is ego on my face, here is Google Earth running in the browser, cross-platform, zero installation, what in my professional career would have required a $20,000 to $30,000 workstation in order to do what I'm able to do here, but does so within the context of the web, so that if you zoom in on a place, you can like use the fetch API to go out and grab stuff off of Wikipedia or whatever for images and descriptions and things. So this is based off of the MVP, right? This is just stuff that has happened over and over again. But we have a very weird world now, right? Growing up, being a little computer nerd, you'd read books and they'd say things like, oh, the computer has a CPU and you write your code and it runs on the CPU and it has a file system. But now we have a heterogeneous deployment surface space that includes on-device, on-premise, in the cloud, edge computing, and there are reasons for doing this. Even when I was back at Parabon, there were people who were concerned about sending their intellectual property to run on computers that we didn't control. And so we had to do all kinds of crazy stuff with obfuscation technologies and whatnot. But you may still not want to actually run your stuff on device or on premises. But with edge computing environments, you can get it close, closer than even regional stuff with cloud providers. And you can decide where to put it. You may want to run it on device. Why? For regulatory compliance. If you're analyzing video to decide if there's evidence that somebody has had a stroke or something, you don't want to take the data off the device because then you have HIPAA regulations that you have to comply to. So if you can send the code down to the device, that eases your regulatory burden. But that's just part of the story, right? Then there's the explosion in hardware heterogeneity, right? Apple's building their own system on chips now that have multiple CPUs, multiple GPUs on them, tuned for performance or tuned for power savings. And their Grand Central scheduling algorithm or engine will schedule accordingly based on battery life. Really remarkable. But we're also seeing things like Snapdragon and from Qualcomm and a bunch of other organizations building very powerful, new, mobile-oriented kinds of systems as well. Now, the reason Apple was able to move to the desktop relatively easily is because they'd hired Christian Lattner. He took over the tool chain, moved away from GCC to LLVM, which is a modular compiler architecture. And just the short version of that is you don't have to do everything all at once. You can write the parser to parse things into an intermediate representation and then still benefit from loop unrolling, constant propagation, dead code elimination kinds of things that we've been doing with C and C++ for decades. But it now can be applied to things like Julia and other languages, Swift and other modern languages that are based upon LLVM. So really, once they got the tool chain in place, and obviously it's a bit of a stretch, but it's not much of a stretch to say they just simply had to recompile, and they could now target ARM-based architectures as opposed to Intel-based architectures, at least in that direction. Going the other direction, they had an emulation that they had to have. Oh, by the way, Clang, which is LLVM-based, has been compiled to WebAssembly. So now I can take code inside the browser, compile it, in this case, down to a 6 kilobyte module. And honestly, I've had Java classes whose names have used more bytes. And I can run it within the browser because the browser is a rich environment. It's got support for hardware-accelerated 2D graphics, 3D graphics, video, peer-to-peer connections through WebRTC, permissioned access to the camera. You can establish data channels between things. And so we have the compiler compiled to WebAssembly to run in the browser, to compile code in the browser to WebAssembly to run in the browser. There's a stack of turtles in there somewhere. So then there's the emergence of RISC-V. Hennessy and Patterson, who coined the term RISC in the first place back in the 80s, wanted to update and modernize the textbooks that they wrote. And the bozos at the large chip companies wanted to license the instruction set to them for that purpose. So they said, forget it. We'll create our own open source ISA, and started teaching around that. Pretty soon they had people saying, wait, why are you changing things every couple months? And they're like, oh, well, after we learn something in a semester, we update it. They're like, yeah, please don't do that. I'm like, well, why not? Because we're building stuff with it. And so RISC-V has become a new open source hardware architecture, and people are innovating faster. I've been following it from the beginning. I've been bullish about RISC-V from the beginning, and we now have people that are producing things that can act as a CPU, GPU, or neural processing unit all at the same time. Now, this is not system on a chip like Apple has, where there are multiple CPUs and GPUs on them, right, including a neural engine. This is one computational engine acting in all three ways. And so we're seeing this explosion of hardware that is going to make more and more computational devices slightly different. And that's where things like WebAssembly and LLVM are really going to make a difference, right? They're going to mediate the heterogeneity in the hardware, which is also something that we have to deal with. We have supply chain attacks that are coming to us through Python dependencies and Node dependencies. And for the overly credulous and non-thinking developers who are generating code that hallucinates dependencies that don't exist, that hackers are saying, I'll make it exist, and therefore these credulous developers are then adding those dependencies so the code compiles. This is a hacker's dream, right, to get into this. So we want to use open source, but we do not want to open ourselves up to this kind of attack. And then there's the whole concept of geopolitics, right? We have chips and AI and these engines becoming more and more things that are part of sanctions and controlled access. China doesn't have access to the ultraviolet lithography that ASML's systems do, at least not at the same level. Europe wants to get away from dependency on other kinds of chipsets. And so IT sovereignty is going to be another thing that's going to drive us to have a wider and wider computational landscape that we're going to have to require things like WebAssembly and LLVM to help us mediate. Now, the vision for WebAssembly always included all of these things, except it kind of seemed like the whole underpants gnome style solution. If you're not familiar with this, this is a South Park reference, South Park from not too far from here, where they were going to collect underpants, do some stuff, and then make money. Not so great in the middle section. But that's kind of what WebAssembly felt like, right? The MVP, do some stuff, and then this vision will come into fruition. And the fruition was, the vision was there. So we had the idea of the MVP, which is just that little section at the top, but how do we make WebAssembly and JavaScript work better together? How do we handle 64-bit address spaces? How do we handle threads? How do we do garbage collection? How do we work with standard APIs? Because what WebAssembly does is it makes your code portable. APIs are what make your applications portable. Why do we need Wine on Linux to run Windows stuff? Because all of those applications were written against Windows APIs. So if they don't exist on Linux, you can't run those applications. Same thing here. Why did that stuff work in the browser? Because tools like Inscripton would basically take low-level standard APIs like POSIX and SDL and OpenGL and OpenAL and things like that, and route them to the capabilities that the browser had. But if you're not running in the browser, you don't have those same capabilities. So up in that right-hand corner, there's a thing that says system interface. Hold on to that thought for a second. But we also have blockchains and cloud-native computing and all the sorts of other things that are in there as well as perhaps embedded devices, Internet of Things devices as well. So there are a series of proposals to extend the platform. But unlike with a lot of software and hardware-based systems where there's a version number that will tell you what you'll get, there is no version number with WebAssembly. Because the use cases are so wide and varied, it's unlikely that every platform is going to need to support all the details. So instead, we have all these proposals that are in various stages of delivery for things like tail call recursion and garbage collection and using multiple memories and SIMD support and 64-bit addressing and exception handling. And the various platforms and everything that need those as they move to implementable phases as specifications, we'll be able to adopt them and support them as needed. However, the W3C does not do implementations. They do specifications. So usually you need somebody implementing these things in order to validate the specifications. And so, interestingly, there was an awareness that this is something that needed to happen, and needed to happen collectively. And so that's where the Bytecode Alliance came into fruition. You may have heard of a couple of these companies. They see WebAssembly and Wasi, which I will mention in a second, as the basis for a modern, secure computing environment that can be desktop-oriented, in-browser, cloud-native, embedded devices, edge computing environments. And they wanted to help take the new standards as they were emerging and support them through a variety of technologies. So one of the first things they did was to make it easy to build Rust-based code that could interact with the browser. And they used a tool called Wasm BindGen. So basically, the Rust code would have code generated with respect to, say, the canvas, right, in the browser, available as Rust code. So your Rust code would call other Rust code, which behind the scenes would call into the JavaScript code to actually interact with the DOM or whatever it was that you're doing. So this is a really fun, cool way of making it much easier to take a language like Rust. So now we can take the benefits of a language like Rust and innovate with languages. One of the reasons why I think Ruby and Ruby on Rails did not take off in the way that a lot of people thought it would is because you had to have the whole ecosystem. You had to have the runtime, and the Ruby runtime just couldn't compete with the JVM and some of the other things that were out there. Now that becomes less of an issue. You can innovate on languages, and using things like LLVM and WebAssembly and tools like Wasm BindGen, connect that stuff up to the browser more easily. The problem was, Wasm BindGen was very rusty in the sense that it had, idiomatic Rust and that idea. And they never intended it to be that way. So they decided that they needed some more support from that. That portable interface that they imagined worked because if you have portable programs, you need the portable instruction set. That's what WebAssembly gives you. And then you need the portable system interface. When you're running within the browser, that's what the browser gives you. But if you're running outside of the browser or outside of an environment that does not have a JavaScript runtime engine, what goes into that box down there? Right? That's one of the things that they had to figure out. And so one of the first things that they did was to create the concept of a POSIX-like WASI environment. So WASI stands for WebAssembly System Interface. And Wasm Time is an open source engine for dealing with WebAssembly and WASI-based systems. So it is a command line runtime as well as a bunch of libraries to allow you to build your own runtimes around this. And that gave them the idea that they could have layered applications. You would write your application on top of versions of libc that were aware of the WASI implementations. They also included in WASI the concept of capabilities-based security. So this was a way of bringing fine-grained access control and things like that into the browser, into the application, as opposed to relying on your environment to do it for you at a fairly coarse-grained and easy to screw up level. So there are versions of libc that are capabilities-based, and that stops because WebAssembly, by the way, has no ability to open files, open network connections, spawn threads, or anything like that. It can only do that if the host environment gives it access to do that. And so what libc on top of the capabilities-based system allows you to do is to say, your code will run, but if you need to talk to the file system, you only get to do so if I let you. And so they were able to build applications, and by having different pluggable backends, kind of like what Google did with TensorFlow.js, but in this case, because of a pluggable backend in LLVM, you could target a WASI environment, but the same code could be a native application, a hosted application, running in a browser, or through polyfills run in a browser in interesting ways. So this is the only code I'm going to show you on the slides here. This is a early WASI tutorial. I encourage you to play around with it because it's fun. At this location, there's some explanation of what's going on. There's also a C program to copy input to output, and a Rust program to copy input to output. So if you create a new standalone Rust application using the cargo tool, and then you overwrite the main.rs that it generated with the Rust from the link I just showed you, you can then quite trivially build a native application that is able to copy input to output. When I do this on a Mac or Linux or Windows, right, it has the permissions that the operating system gives me. I'm running it. It's able to do so. If I run it, I need an input and output file, so this just triggers the usage. But then if I say, OK, here's a file called hello.txt, run it, and copy hello text to temp, it works, because on my machine, when I'm running a native application, I'm allowed to touch those file systems. But all I need to do is to recompile it with a different backend, a Wasi-based backend, a WebAssembly Wasi-based backend. Now, there are different runtimes. Wasmer is a runtime. Wasmtime is a runtime that support Wasi. You can just say, run that module. The the usage statement comes out. Hey, you need to give me an input file. OK, here you go. Here's the input file. Boop, you can't do that. You don't have permission to access the file system. So we took a native application, recompiled it with a different backend, and suddenly it can no longer do things that I don't want it to do. Now, the Wasmer and Wasmtime runtimes have a simple way of indicating which directories you have access to. So you can just say you could use the current directory and the temp directory, and now rerun it, and it'll work. So we get portability. We get the ability to target different platforms, but we don't have to rewrite the code in the process. And so that's what Wasi brought us initially, and that was pretty amazing. But then they stopped and thought, is POSIX-like enough? Because POSIX is a very C-oriented set of APIs. It deals with like pointers and things like that. I mean, it's very elegant, portable code. That's why a lot of tools work on Linux and Windows and Mac OS and other environments. But they decided they needed to do some more research. And one of the things they came across was Mark Miller's PhD thesis called Robust Composition. And one of the interesting things about that is he indicated that this was the intersection of capabilities-based security and software composition worked hand in hand. It wasn't either or. They helped each other. So the goal that they basically took from reading his thesis was that they needed cross-language interop. They needed component isolation. WebAssembly modules only allow you to import or export shared memories. But if you export a shared memory, there's no reason somebody else can't overwrite what's in there. Now, if you're just taking a standalone application and compiling it to run in WebAssembly, that's not a problem. But if you're trying to build tools and libraries and reusable code, then that's a problem, because you could now have something that you want to be isolated, and you integrate it with something else, and it could completely corrupt your memory. So they wanted to have the promise of WebAssembly sandboxing for the components as well, and also the ability to virtualize the interfaces. So I'll come back to that, but just take a step and think about that. You could have a Wasi-based implementation of something that required a file system running in a browser that virtualized file access to either local storage or, say, to an S3 bucket. The application is unaware of this. It's just writing to a file abstraction. But the configuration and the layering and the virtualization of these capabilities is going to make the code even more portable. The idea that two components that are designed to work together or have services that one needs from the other, you can compose them into a single complete component now. And so the idea of saying, hey, I have needs, you have the solution, let's create a standalone thing that does what I do then, is part of the story. And it can happen incrementally. So I could compose two modules that solve maybe 3/4 of my needs, and then expect a third or fourth component to provide the others. This doesn't have to be done all at the same time. So these commitments to capabilities-based security then allow us to share handles or resources for non-fungible tokens, not string representations of like file directories or file directory names or IP addresses or things like that, which are easily spoofable or corruptible in any number of ways. So after a lot of research and thinking, the Bytecode Alliance team came up with this idea of what they called the nanoprocess module. Nanoprocess architecture. And the idea, you can start to see, as John was saying, this starts to look a little bit like microservices. But the problem with microservices is, even though they are very composable, it usually involves taking some internal representation, serializing it to JSON, sending it across a network connection, deserializing it into some other representation on the other side, and that's just too painful. But when we can have components that can be composed together through this process, then I don't need to deserialize the data if I can just pass handled references to it or some other higher level structure. So we need a way of expressing higher level structures more than just numbers. And so that's where the WIT IDL that I'll mention in a minute comes in. But this was the vision that pushed them towards realizing that they needed to develop the component model. So the terminology is that components are containers for WebAssembly modules or other components. We're not throwing away the core WebAssembly core stuff. That does great stuff. We are just now wrapping it with the ability to express needs and satisfy requirements. So we can express the imports and the exports that we need through the WebAssembly interface type interfaces. But this is also where we describe the other things that I'm about to mention, like worlds. Worlds are simply surface areas of combinations of one or more components. A world will say, I accept, or I require these kinds of interfaces, and I provide these kinds of interfaces. But now, guess what? We can reason over what the component needs. And if it doesn't say it needs a file system, or network access, or access to a GPU, then we know, okay, this is a limited environment demand on the hosting environment that it's running on. So we can start to reason over these things in fairly powerful ways. And then packages are just collections of WIT files that allow us to easily tie these things together into kind of an expressed combination of these files. Components are linked parametrically. The POSIX view probably would have had to have us passing around pointers, which would have been very dangerous, but also based on studies from ML module systems and whatnot. They saw that parametric linking with a type system of value types can be passed from one interface to another with no more knowledge of what's going on behind the scenes of either one. So that's the other part of WIT, is that allows us to define a bunch of built-in types like strings, dictionaries, lists, vectors, stuff like that, but then also domain and user-specific ones like records and variants and things like that, with subtyping built in there as well. So we can now describe functions in terms of the types that they accept and return in a language-independent IDL, and then rely on tooling like WASM bindgen, except that was just Rust to JavaScript, to now be using things like WIT bindgen. So WIT bindgen is now a way of generating the WIT files into native language bindings so that your Rust code, your JavaScript code, whatever, your Ruby code, your Python code, can have idiomatic language bindings to what it's providing and what it's returning. And that way, nobody has to rewrite this multiple times. You write a tool that generates what you need, and that's what we're seeing now. I encourage you to go through this tutorial, because right now, the Bytecode Alliance is extremely open. All their meetings are available on YouTube. All the documentation and the specs and the meeting notes and all that kind of, you can attend if you want to. But there's not an easy to follow path. And as they change their minds on things, it gets a little confusing. So there's good news coming on that front as well. But basically, what I'm doing here is synthesizing the last 5 years or so of developments in these technologies and catching you up to what's happening. But in this tutorial here, you'll see that they motivate the model, and then they go through the concept of creating these components. So if I go to the Rust component one, and I'll make this a little bit bigger, there is a Rust tool plugin for Cargo that makes Cargo WebAssembly component aware. We want to reduce the friction between existing tools and their support for WebAssembly components. So this is just a cargo plugin that's aware of components and their structures. So you can generate a component and give it a package name, and then in this case, we're just creating a number, a way of adding two numbers together, which, let me be clear, you would not use WebAssembly components to do that. But just to keep the mechanics simple, all you really have to do is to provide a function that does that, and then the whole tool chain will tie that together into a standalone component. Now, in this case, this module simply exports a function to add two numbers together, but then you go through and you build a calculator. A calculator needs the ability to do addition, so it has the need for an addition function, but then it exports the ability to do arbitrary expressions. And so it has the ability to say, take 2 plus 2 and then produce a result, because you have a component that you can compose into a calculator component that provides those behaviors. So just trying to give you a little quick sense of what's going on. This is a good tutorial to kind of work through on that front. So here's where we are. I know you can't read that, but at the bottom there is a link that I encourage you to read. Bailey Hayes has a nice write-up, and she's also got a good video linked to there as well. And in it, you see that there are three main tracks to what's going on. There's the core WASM platform, which is continuing to evolve to support the various proposals that I mentioned earlier. Then there's the component model. Part of the reason why it seems like WebAssembly was really exciting and then nothing happened for a while is because they realized they had to fill in the underpants GNOME middle section. And they spent the last couple of years doing that. And, oh, by the way, there was a pandemic and stuff like that as well. So it slowed them down, but they're now at the point where they realized the early Wasi approach was not the approach that they wanted to take. So just this past February, they released the 0.2 version. I apologize in the description of this. I had a brain fart when I was writing up the abstract, and I said 2.0. It's the second preview, but its number is 0.2. There is a plan for a 0.3 that I'll come back to in a minute. But basically, this was the work to finalize the component model. And that enables everything else. So now that that is done, a bunch of other things can be done on top of that. But they can start to build some of these early Wasi interfaces, combine them into what are called worlds, right? And so in this case, we have a Wasi command line interface world. What kind of tools, what kind of expectations does something running in that space require? Access to standard in, access to environment variables, access to stuff like that. So a bunch of existing interfaces can be combined into a CLI world, and there are two worlds that were part of the 0.2 release: the CLI one and the HTTP one. So what does the HTTP world have? That has things like HTTP request handlers, or the ability to open up new connections and things like that. So those are in place. We have new tooling like JCO, which is to JavaScript what WASM time is to other languages. So JCO can run Wasi component-based components and libraries and things. But it also allows you to take existing WebAssembly modules and components and transpile them into JavaScript so they can run in the browser or in Node or Dino or something like that as well. So 0.3 will come out sometime this year. I don't know exactly when. But that's going to add support for futures and streams, which is an important part of the ability to support asynchronous handling. And they're going to provide an asynchronous mechanism and a low-level control flow mechanism so that you can have components written in different languages against different asynchronous engines that coordinate and work together in composed forms in a cross-platform kind of way, running on the back of the WebAssembly runtime. That's freaking magic. Now, is it going to work? All signs point to yes, because there are people who are doing it already. Golem is today is the presentation. There's a Golem presentation about the component model. Microsoft and Fermyon and a bunch of the other environments, members of the Bytecode Alliance, WASM Cloud, have been building stuff around these things, and they're being very successful. So the signs look good. But given everything else that I said, hardware heterogeneity, the deployment model heterogeneity, the problems with security, the problems with all these other things that are happening, and honestly, all the layoffs in our industry are a sign that we have not been providing the value that we could have been. And I think we're going to need to move to the, I've somewhat cynically said people who get paid to build stuff don't mind getting paid to rebuild stuff. That can't work anymore. And we're going to need to take advantage of the benefits of software composition. Why is Unix so awesome as a tool environment? Is because of the software composition around the file system. My environment, my presentation environment here that I don't have time to go into, is a similar sort of thing, but it's around resource abstractions. And so the ability to do that kind of software composition around not just a single abstraction, but a series of abstractions that work in different environments is part of the plan that is going to make things, I think, more likely to succeed. So the last couple of slides, I'm not going to go over much other than these are the Wasi interfaces that are currently supported in the O2. There are worlds, the HTTP and the CLI worlds are the only ones that are there. But in the very near future, when O3 comes out with support for futures and async and streaming and whatnot, the other ones will be there as well. But there's also interfaces, Wasi interfaces for things like WebGPU, or Philips I2C protocol, or neural networks, or key value stores, or cryptography, or virtualizing the entire thing. So now take a step back and think. If you have a component model that provides the imported needs of something, it has no clue what that is, what your implementation looks like, and we can now completely virtualize things like file systems and network traffic, and we can now mock things without having to have a dependency injection framework. We can do all kinds of cool testing stuff around this. So these are all separate initiatives that are emerging now that the component model has been standardized and stabilized. There are special interest groups that are emerging. So the guest languages one is the most active. And so JavaScript and Python and Go are all very active in there. There's Ruby is now an engine. There's a Wasmtime engine around Ruby. But Microsoft.NET is part of the guest language initiative as well. It's earlier stages, but this gives you a sense of the scope of where these things are going. Then we've got other languages like Zig and Grain and other things that are emerging that work nicely with WebAssembly that we expect to see support there too. The documentation SIG, thank God, right? Because their openness is a tribute to their approach to collaboration, but it is impossible to find anything if you're just getting started. So the documentation SIG is going to start coming up with better, more easy to access documentation as well as tutorials and things like that. But there are SIGs that are emerging for embedded systems, debugging WebAssembly and component models, and registries. And what do I mean by registries? WARG is an attempt to solve some of the issues that we've seen with other supply chain systems. They're going to provide transparency so that you can see when things have CVEs and whatnot against them, and all kinds of cool support so that it's not a big pain in the ass to be secure and deal with this. So again, they're not just trying to barf out an NPM replacement. They don't want a single organization like NPM to control everything. You'll be able to set up your own WARG repositories and pull things across different, here's my local version of something that satisfies the needs of something from a central repository. So if you have very specialized needs in your organization, you can deal with that as well. So a bunch of other containers for you to check out, but this is really the trend that we're on, right? And this is what John was talking about. You used to buy your computers, set them up, do all this stuff yourself. Then we virtualized that and called it cloud computing, the hardware. Then we used containers to have the expectations of what they needed on there. Then WebAssembly said, yeah, but it doesn't even matter about native libraries anymore. And now the WebAssembly component model, this is a slightly older image, but the component model is going to say, if you have the capabilities that you need to satisfy your business requirements, and you can have a runtime that can spin up in nanoseconds, then things like serverless functions become even more interesting. and we can get down to what is the cost of computation. You don't have to have resources sitting around waiting for inputs. You respond to a request, you spin up quickly enough to answer the request, and you shut back down. That's the cost of computation that you need to pay for. I hope you've enjoyed this. I hope you dig into this and look further. Please check out the other WebAssembly talks. There's a nice variety of them today, and enjoy the rest of the conference.